you very much. Thanks for the invitation, Sean. Okay, so this is based on joint works with Liam Hanany, who is my student in Tel Aviv, and Ori Parzanchevski, who is currently in Jerusalem. Okay, let me start with just defining what are the permutations what are random permutations induced by free words. So we call them W random permutations. So we fix a word in the free group F. For example, W equals xy to the minus 2. We sample, in this case, 2 permutations from Sn. They are going to be uniformly random and independent, and we plug them inside our word to get a random permutation. So in this case, we get sigma tau to the minus 2. So this is our W random permutation. This is the object we study. And I want to mention a few challenges we have. These are very vague. So first of all, we want to find a structure in the W measure on Sn, or in the measure of or the distribution of a W random permutation. And I'm going to talk about such a structure. And then there are two. Here's another question that one may consider. Which words induce the uniform measure on Sn for every n? Okay, so for example, is this random permutation, does it distribute uniformly? And more generally, if you take 2 different words, do they induce the same measure on Sn for every n? Or put otherwise, when is it true that 2 words induce the same measure on Sn for every n? So these are the kind of challenges that we have. Okay, so this talk will have 3 main parts. In the first part, I'll talk about an older work about average number of fixed points in a W random permutation. In the second part, I'll talk about a more recent work, which has to do with other statistics. So for example, the expected number of 2 cycles, or any other local statistic of the permutation. And in the third part, I'll explain how this is all related to spectral gap of random Schreier graph of Sn. Okay, so this is the plan. Please stop me if you have any questions. I mean, even if there are stupid ones, feel free to ask, unless you don't want it to be on YouTube. Okay, so let's start with the fixed points of W random permutations. So we'll denote here by C1, C for cycle. So cycles of length 1 of sigma. C1 of sigma is going to be the number of fixed points in the permutation sigma. And we denote by EW of C1 the average number of fixed points in a W random permutation. Okay, so now there is a by now rather old result of Nika from 1994, which proved 2 things. I mean, his result was much more general, but the main themes of his results are, first, that his expected number of fixed points is a rational function in n. And I will explain it shortly, why it is so. Okay, let's look at some examples. So I have here a list of words, and for every word, I'm going to mention the expected number of fixed points. Okay, obviously, if the word is just x, you just get the uniform measure. For uniformly random permutation, the expected number of fixed points is 1. This is a simple exercise. What if you take a square of a random permutation? Then the expected number of fixed points grows to 2. This is also an exercise. Okay, what happens if you take the commutator of 2 letters and you take the square? It turns out that in this case, you get this more complicated rational expression. Okay, this expression holds for every n bigger than 4. I mean 4 or larger. This is the expected number of fixed points. For xy squared, you get 1. For this word, you get this number. And for this word, you get this number. Okay, so you get for every word the rational expressions that is true for every large enough n. Okay, this is the first part of Nika's result. The second part, he asked what the limit is. So what is the free coefficient So here the free coefficient is 1, here it's 2. You see that so in this case, here in the example, we have either 1 or 2. The general theme is that if W is a power, if it's a dth power of U and U is a non-power, so this is the maximal power, then the expected number of fixed points at the limit behaves like the number of divisors. This should be a divisors of D. Okay, so if it's a square, you have 2. If it's a cube, you also get 2 in the limit. So I want to explain these two results now, why they are true. Okay, so let's first talk about the rational function. So here's an example. We'll prove it by example. Let's look at the commutator word. I want to show that the expected number of fixed points is rational. So here is how you compute it. If let's say if I is a fixed point, I is a number between 1 and n. If it's a fixed point of the random permutation generated by x and y, then it means that it goes through some 4 elements between 1 and n. In this example, I, j, k, and l, I call them. And the permutation x maps I to j, L to K, and the permutation Y maps I to L and J to K. So in this way, if you go over the word, in this talk, I'm going to multiply permutations from left to right, okay, just for convenience. It doesn't really matter. So if you take this, if X and Y are some permutations and I is a fixed point, it means that X takes I to some J, then Y takes J to some K, then X inverse takes K to some L, and then Y inverse takes L to some I. Okay, so you go over all 4 tuples of elements from N, and you ask what's the probability that 2 random permutations satisfy these constraints. Okay, and this can be computed in the following way. So we just divide into cases depending on whether I, J, K, and L are the same or not. So the first case is when they are all distinct. If they are all distinct, I claim that the expected number of fixed points where they are all distinct is exactly this expression. Why is that so? So the numerator, you see, I just picked what are I, J, K, and L. I know they are all distinct, so this is the number of choices I have to pick I, J, K, and L. And then once I pick them, I know that X is a random permutation, which should satisfy 2 constraints. It should map I to J. This happens with probability 1 over n. But then, in addition, it should map L to K. So this happens with probability 1 over n minus 1, because I already know that I is mapped to J. So this is the probability that 1 over n times n minus 1 is the probability that a random permutation satisfies 2 constraints. And this is the same probability for the second permutation, for Y. So this is the first case. Okay, so the second case, just as an example, is when I is equal to J and K is equal to L, but they are different. These 2 pairs are different from each other. So I draw it as a graph. It's going to look like that, like so. So I have this vertex is I and J. So now X, and this vertex marks K and L. So now in this case, I have 2 vertices. I need to choose the value of I and J, which is I have n possibilities, and then value of K and L, I have n minus 1 possibilities. Now X, in this case, has 2 constraints. So it's 1 over n times n minus 1, and Y has one constraint. So it's 1 over n. And you see that, indeed, what's important in this graph is if I go starting my vertex corresponding to I, and I follow my word, so in this case, it's X, Y, X inverse, Y inverse, I return to the original vertex. Okay, so this is the contribution of this case. Now there are 5 more cases in this example. I'm just going to draw the graphs. These are the 5 additional graphs. Each one of them, you can compute immediately what's the contribution of this case to the expectation. You sum it all up, you get this expression, 1 plus 1 over n minus 1. Okay, and obviously this works for every word, and this is the proof of of the first result that this is a rational function in N. Okay, and any questions? Okay, so now let's go to the second result of Nika, which is the following, which is the result about the limit. So Nika said that if W is a d-th power and not more than D, then in the limit, you get the number of divisors of D. And why is that? So if you look at these graphs, let's see if it's going to write. Okay, so look, for example, at this expression corresponds to this graph. So the first case. So what do we have here? We have roughly the numerator, the numerator is roughly n. Okay, it's not quality, this is roughly n to the number of vertices of this graph. And the denominator, you have one factor for every edge of the graph. So this is roughly n to the e. Okay, so the contribution is roughly n to the v minus e. And these are all graphs which are not trees because they all have they are all covered by a closed cycle, which is W, which reads W. So they are not, none of them is a tree. And so at the limit, this graph has some contribution if and only if v minus e is 0, namely if and only if this graph is a cycle. So you get, so the limit, we get the limit is the number of graphs which are cycles. And this is exactly the number of divisors of D because we need a cycle such that W forms a closed walk on this graph. So for example, if W is U to the D, we have a one graph that reads U. We have a second graph which reads U squared, and then W. So here W circles 6 times, here it circles 3 times. We have this graph, and we have this graph. Okay. So this is roughly the proof of this is the proof of the second result of Nika. Okay. So now, okay. So now what we know in particular is that if W is a power, we know something interesting about it. But what happens if W is not a power? Can we say something intelligent about the rational expression that we get? Okay, so this is the question. We always know that we have the limit is going to be 1 if W is a non-power. The limit is 1. So if we subtract the 1, what is the order of the deviation from 1? What is the order of the expected number of fixed points? -1 for non-powers. Okay, so let's look again at this example. Okay, so now I drew these graphs based on V minus E. So this is the graph that contributes roughly 1. These graphs in this line, in this row, contribute roughly 1 over n. And this graph contributes roughly 1 over n squared. So it turns out that the right way to solve it is the following. So first of all, we need to think of these graphs not just as graphs, but as subgroups of the free group. So these are graphs that are sometimes called core graphs or Stolling's graph. So how do they correspond to subgroups? You look at the vertex corresponding to I. This is the first vertex of where your word, the path of your words begins. And then you look at all closed paths that start and end in this vertex. So for example, here you have x, y inverse. That's an element of the group. If you take all the closed path at this vertex, they form a subgroup of the free group. And there is a very immediate relation between the order of contribution of this graph, or the order characteristic of this graph, and the rank of the subgroup. Okay, so this is a subgroup of rank 1. Here you have subgroups of rank 2. And here this is a subgroup of rank 3. Okay, and it turns out that when you look at these expressions, these rational expressions, you have cancellations. After you subtract the 1, you have cancellations all the way down until the first time you see a group where your word is not primitive. So a primitive it means that it is part of a minimal generating set. Okay, I see there is a question from, I don't know if it's new or not. Yeah, actually there is a proof in this case for, I mean, Rudy asked whether 1 plus 1 over n minus 1 deserves a cases-free proof. There is a proof for this particular word, but not for other words with the same expression. So I don't know. Okay. Okay, so let me explain what I mean. So here, this group is actually as a subgroup of the free group. So every subgroup of a free group is also free. This one is actually just, oops. This one is actually generated by W, by my word. Here, this one is generated by X and W. Oh, let's write it. Okay. Okay, and so on for all of these. Actually, for these 6 subgroups, I can write a basis, a minimal generating set, which contains W, the commutator of X and Y, but not for this one. So the commutator of X and Y, I mean, this graph corresponds to the group F2, just the whole group, the whole free group in this case. And it turns out that W is not primitive here. And this is the reason why, it turns out that this is the reason why the deviation from 1 is of order 1 over n. There are cancellations up to this level, except for this graph. Okay, so let's make it more formal. So we call this quantity the permittivity rank of a word. Okay, so first we start with, this is a generalization of power. So let's describe a power in a different way. So if W is U to the D, is a power of, is U, where D is at least 2, if W is a proper power, another way to say it is that W is contained in the subgroup generated by U. So it's a cyclic group, this is just Z, but it is not primitive. It's not part of a minimal generating set of U. Right, because the only generators of U, the only generating sets of size 1 of this subgroup of Z is U and U inverse. And we call this permittivity rank 0 and denoted by pi tilde of W equals 0. Okay, so what is the next phase? The next phase is permittivity rank 1. So first we want to rule out the first case. We want to rule out that W is not a power, which means that in every subgroup which is generated by a single element and contains W, W is going to be primitive. In other words, W is not a power. But there is a subgroup generated by 2 elements, so it is of rank 2 where W belongs, but not as a primitive element, not as a minimal generator. Okay, for example, XY belongs to the subgroup generated by X and Y, the ambient group F2, but not as a primitive element. So its permittivity rank is 1. So here is the general definition. The permittivity rank, we look at the maximum R, the maximum integer R, such that whenever W is contained in a subgroup of rank at most R, in the free group, W is going to be primitive in this subgroup. So in other words, if you look only at subgroups which are of rank R or less, we cannot see that W is not primitive. W, if we only look at these groups, W looks like a primitive element. So they are cancelled, and they are okay. So this is denoted by pi tilde, permittivity rank. Okay, these are the possible values of the permittivity rank of words inside the free group F. Okay, what is -1? -1, it means that even in groups of rank 0, even in the trivial group, my word is not primitive. So this has to be the identity. Only the identity belongs to the trivial group, and it's not a primitive element there because the minimal generating set of the trivial group is the empty set. Okay, 0, these are powers. Why do we stop at rank F -1? Because every word, if it's not primitive in the ambient group, then F itself is an element which doesn't satisfy this. So F itself, which is of rank in rank F, W is not going to be primitive there. So this is why it stops at rank F -1. What happens if W is primitive in the ambient group in F? Then it turns out that it's primitive in every subgroup, and then we get infinity. Okay, so infinity is only for words that are primitive in the ambient group F. Okay, so let's go on. So this is again the definition. So what's the connection to expected number of fixed points? So I said it without writing. So this is the theorem with Parzanchevski from a few years back. So the expected number of fixed points -1, it's of order 1/n to the permittivity rank of my word. And the numerator here, we know it exactly. It is exactly the number of subgroups which are the witnesses for the permittivity rank. So these are the subgroups of which are of rank 1, the permittivity rank +1, where W is no longer primitive. And it turns out that there are only finitely many such subgroups, and we have a contribution of 1 for each such subgroup. Okay. So I'm not going to speak much about the proof. I'm not going to speak at all about the proof of this theorem. So the challenge here is to show that there are all these cancellations that continue all the way as long as W is primitive in all the subgroups. So I'm not going to speak about the proof, but let's see what it tells us. It tells us that there is this categorization of words in the free groups. We have first words of permittivity rank -1, which is 1. And for this word, the expected number of fixed points -1. Okay, obviously the expected number, if W is 1, we always get the identity permutation. We have n fixed points. So we have n -1 for the expected number of fixed points -1. If W is a power, this is Nicker's result. We know that even when we subtract 1, we still get an integer because the limit is the number of divisors, which is strictly greater than 1. So this is theta of 1. Permittivity rank 1, so here are two examples. This is roughly theta of 1/n, and then it goes on until the highest finite rank, permittivity rank, which is the rank of F -1, where this is the order of expected number of fixed points -1. And it turns out that a random word is going to be of the maximal possible permittivity rank, finite permittivity rank. So a random word, it means if you take a random word of length 1000, then almost all of them will be of this permittivity rank. And finally, as I said before, permittivity rank infinity means that W is primitive. And when W is primitive, this is actually, so what the theorem says, if you plug in here infinity, you see that you just get 0. And so the expected number of fixed points -1 is 0, but this is actually very easy to prove without any of that, because if W is primitive, it's an exercise to show that if W is part of a basis, a part of a minimal generating set of F, it's an easy exercise to show that it induces uniform measure on Sn. So a W random permutation is just uniform. So we get from this, actually we get an answer to one of the questions I raised in the first, perhaps in the second slide. which words induce uniform measure on Sn. So these are precisely the primitive words. I mean, we know primitive words induce uniform measure. This is, as I said, an exercise. But from this table, we see that if W is not a primitive word, then for large enough n, the expected number of fixed point is going to be strictly more than 1. Therefore, the measure is not uniform. Okay. Okay. Any questions so far? Okay.
Can you remind? Is there a simple way to check whether a word is primitive?
Yeah, there is a. Okay. First of all, you can do that. I mean, you can draw all these graphs and compute the expected number of fixed points. This is a very non-efficient way. There is an efficient way. There is an algorithm. There are a few algorithms. The most efficient one is due to Whitehead from the late 30s. So he has some algorithm, yeah, which I don't. It's not hard, but it's not very easy to explain in 1 minute. Okay. Okay. So let's move to other statistics. So as an example, let's look at the expected number of T cycles, and I denote it by C of T. So first, the number of fixed points is C1, and the expected number of CT, the number of T cycles in the uniform permutation, is 1 over T. Okay, one way to see it is that I guess some of you, okay, you probably know that, but if you take just the element 1 in the random permutation, the length of the cycle in which one belongs to is uniform between 1 and n. So it's going to be in a T cycle with probability 1 over n. So the total number on average, the number of elements that belong to a T cycle is 1. But we counted every T cycle T times. So we get 1 over T. So together with Liam Hanany, we generalized these results about fixed points to other T cycles and other statistics. Now, for this theorem, we assume that W is a non-power. And we ask what is the deviation again from the expected number of T cycles in the uniform. What is the expectation? What is the deviation from the uniform measure? So this is the uniform. This is the deviation from the uniform. And it turns out that again, it has to do with the permittivity rank. But there is a +1 here. You see, there is actually one. There is a gain of 1 more degree, 1 more in the exponent. So this is actually a more general phenomenon. I mean, the cycles is just something that everyone can understand. More generally, I mean, in case you know some representation theory of Sn, this is the real phenomenon. If you take, this is a family of, so this is a Young diagram. It corresponds to some irreducible character of Sn. So if I take a family of irreducible characters for every n, okay, this should be capital N. So how do I do it? I take the first row should be very long, of size n minus k, and I fix some lambda of size, say, k, outside the first row. So this gives me a series of representations for Sn, for every n which is large enough. If I take the expected value of this character on my random permutation, double random permutations, I get the same bound. And this is equivalent, actually. So from this more general result, I can say let's say intelligence things about every polynomial in the small cycles of my permutations. So how exactly do I do that? So every such polynomial, I can express it as a sum of such irreducible characters. And I just need to find out first the coefficient of the trivial character. This will be the expectation over the uniform measure. This is like the 1 over T here. And then I have the coefficient of the character of where lambda is just 1 cube. And then then I take this result. Then I'm going to get my coefficient times this coefficient. the coefficient of this standard character times this degree, and then all the rest is going to be of smaller order. Okay, you see here I had to take k at least 2 because when k equals 1, this is actually the number of fixed points, -1. Okay, so this is our more recent result, and but we conjecture that there's actually much that the truth is much how do I say it? The real result should be much stronger, or the order should be much smaller. You see, we think that the truth is that if you take the expected number of a character, where you have k of some character, is going to be 1 over the dimension of the character, not n, the dimension of the character to the permittivity rank. Now, the dimension of the character, when you have such a family of, when lambda has k cubes, when you have k cubes outside the first row, the dimension of this representation is roughly n to the k. So the dimension of the character is roughly n to the k. So we think that this is the real, this is the truth. For example, so this means that the expected number of T cycles should be again 1 over T, but then 1 over n to the T times the permittivity rank. Okay, because it turns out that if you take CT and you write it in terms of irreducible characters, you only get characters which are of dimension with T cubes outside the first row. Okay, so I want to next say something about the proof of this result and how it relates to the previous result. Okay, so
just a second, you know how to prove this conjecture for some specific W, like the conjecture you just stated?
Okay, good question. Yeah, or perhaps I should say more generally why we believe this conjecture. Okay, perhaps I should remark about why we believe this conjecture. So first of all, yes, it is true for several words. It is true for for the commutator word. It is true for product of different commutators. It is true for powers. For power words, it is trivial because permittivity rank is 0. But it is also true if you take 2 words with different letters, so this joint set of letters, and you concatenate them, and the conjecture is true for one and the other, then it's true for the concatenation as well. So for example, it is true for x to the 5 times yz, or even w, or even ts. Okay, so it is true for a commutator, therefore and it's true for powers, therefore it's also true for this word. So this is one reason we believe this conjecture. We also have we made some simulations. We conducted some simulations, although not very many of them. They so far agreed with this conjecture. Another reason is that perhaps at the end of the talk, I will mention what happens in other groups. If I don't speak about symmetric group, but about other groups, say unitary groups, then we have such a phenomenon where you see that the expected number of certain families of characters behave like that. It has to do with so you take the dimension, you take 1 over the dimension of the character, and then and the exponent has some, not necessarily the permittivity rank, but some invariant of the word. So you have such a phenomenon. And finally, another reason we believe this conjecture is that after we stated this conjecture and tried to prove it, we realized that it implies some conjecture, perhaps general conjecture about it's in combinatorial group theory. Perhaps I'll explain it a bit, or geometric group theory, which I'll explain a bit soon. And it turns out that some other group of researchers had exactly the same conjecture from a completely different point of view, from completely different motivation. So Lars Lauder and Henry Wilton, which happened to, so Henry is also in Cambridge. They came up to a to the same conjecture with different motivation, or from different point of view.
You mean the SCL stuff, yeah?
Yeah. So what is something that is analog to SCL? Yeah, something which is has to do with stable permittivity rank.
Yeah. Yeah. Great. Yeah.
Like okay.
Yeah. Thanks.
So are you conjecturing the lower bound here as well, or is it just the upper bounds conjecture?
Okay. I mean, if I learn from what happens in UN and SCL, then perhaps this would not be exact for every character, but perhaps if I go over all characters and I take that at least in one of them, it will be exact. But this is stronger. No, okay, sorry. This is actually okay. Sorry, this is no. I mean, okay. We know that for some characters this is true. It's true in this character. But we can even say that it's true for infinitely many characters. I would guess, but okay. So I want to say something about the proof of this result. So if we want to compute, let's start with just the expected number of 2 cycles. So what we need is to compute. We look at this graph this time. So we have here 2 vertices. We have W and W, and so we wanted V1 and V2 will correspond to the 2 elements in the 2 cycle. So if I carry out the same computation which we had before for the fixed cycles, for the number of fixed points, we need to look at all the quotient of this graph. So we merge some of the vertices together, but we always keep V1, V2 apart. Okay, because if they are the same, we just get just a 1 cycle. Okay, so if we want them to represent 2 different elements between 1 and n, and everything should be up to a factor of 1/2, because if I do the same computation exactly, I would count every 2 cycle twice. But this is not really important. So I thought this slide would be better if I just write it down to make it a bit slower. Okay. So again, if we take all the quotients. All quotients of this graph. So again, these are going to be graphs which also will represent subgroups of the free group. But so it turns out that there is, so this is a very rough, this is not exactly what I'm going to write, but roughly there is cancellation as long as W squared this time. So now we have the element W squared is primitive. Okay, so we need to, so we look for subgroups H of the free group such that W squared is in H and not primitive. So W squared is not primitive in H, but also W is not in H. Why W is not in H? Because we have this condition that V1, V2 are not the same. Okay, if W is a closed cycle, it means that we identified V1 and V2, and this is not allowed. Okay, and then it turns out that there is exactly the theorem we need. Okay, perhaps I'll say that. So so the claim is that rank of H is at least the permittivity rank of pi of the permittivity rank of W plus 2. Okay, so remember, if W, if I just do it for W, and so if W is not primitive in H, then by definition, rank of H is at least the permittivity rank plus 1. by definition. Here I'm saying that again one more, and from this you can get the result. Okay, so I'm just going to prove this to mention what's the argument behind this proof, behind this claim. So this is quite immediate if you use a classical result by Baumslag and Steinberg from 68. So they say the following: if H is free, H0 is an element, and let's say you add a square. You want to take H and add a square. So what does it mean? You add a square root, the square root of H0. Okay, perhaps I should say before that H0 is not a power and non-primitive in H. So if you take a square, it means, what I mean is that you look at H, you take the free product with another element, let's call it X, and then you divide. You want X to be the square of H0, so you want to divide by this equation, X squared equals H0. So you have here some group, and then you take sorry, let's denote this by J. So J is not free, but the theorem is that every quotient of J, which is a free group, satisfies that its rank is smaller than the rank of H, strictly smaller. Okay, so in our case, so again, we have this H, it's a subgroup of F, and W squared is an element, but W is not. So W squared is has no root there. So let's take so we'll take H, the subgroup generated by H and W. So we add W to our group. This is obviously a subgroup of our group. Now this is in this group, W squared has a root, W. So this is a free quotient of this J. Therefore, its rank is strictly smaller than the rank of H. Okay, but it's easy to see that W is not primitive. I mean, in this group, W is contained, and it is not primitive. Why is it not primitive? Because if it was primitive here, then we could take a basis for this group which contains W, and then in H, it would just mean that W squared must be primitive in H. Okay, yeah, I don't have much time, so this is an exercise. I mean, and therefore, we know that the rank of HW, by definition, W is not primitive there. This is strictly more than, this is at least the pi plus 1. The primitivity rank of W plus 1. And rank of H is strictly larger than that. Therefore, its rank is at least pi plus 2. Okay, so from this, as I said, we get, so this proves the claim, and from this we get, after some more considerations, that the expected number of 2 cycles minus 1/2 okay, and I'll remind you that we conjecture that shouldn't be pi plus 1, but 2 times pi. This is the truth. And so perhaps I'll mention it. We conjecture that 2 times pi, which means, so if this is true, then it implies the following conjecture that in fact that the rank of H, so the same H here, so it means that there should be some strengthening of Baumschlag-Steinberg theorem, not in perhaps this general assumptions, but in our case, it should be at least twice permittivity rank. Okay, and this is general conjecture. I mean, this is one incidence of the general conjecture that Wilton and Lauder also conjecture. Okay. Okay, I don't have much time left. I want to say what happens in another aspect of this picture. I'll just say very briefly. What happens if instead of the number of 2 cycles, you take the expected number of C1 square, so the number of the expected number of the fixed point squared. So in this case, you need to analyze this graph. When you have 2 W's, so here your graphs are not necessarily, the quotients are not necessarily connected, but if they're not connected, it's easy to guess what you need to expect. You need in one of the cases W not to be primitive, but what happens if you connect them? If you connect them, let's say you have one graph, which is a quotient, so now you have here I, and you have some, this is W, and you have J. So what is the condition which parallels the imprimitivity? So here you want that this element W and some conjugate of this W together would not be part of a basis of this subgroup. Okay, I mean, this is very fast, but I don't have much time. Oh, I'm really out of almost, I have like a few minutes left. So let me say very briefly say something about random Schreier graphs, which is how do you use these results to study random Schreier graphs of the symmetric group. Okay, so what is a Schreier graph for the symmetric group? So we look at the action of Sn on S tuples with respect to, say, 3 permutations. So what is this graph? Okay, so the vertices are the S tuples of different elements from 1 to n. So this is the number of vertices. In this case, we have 3 permutations. So we have, for every tuple and each one of the 3 permutations, we have an edge between the tuple and the result of applying the permutation on this tuple. Okay, so this is going to be a 6 regular graph. Because from every tuple, we have every tuple is connected to its image under sigma and under sigma inverse for each one of the generators. So this is a 6 regular graph. And what is a random Schreier graph? You just pick these 3 permutations at random, uniformly. So this is 3 is just an example. In general, you take d over 2 permutations, and this generates a d regular graph. Whenever you need at least 2 permutations. Sorry, d over 2 should be at least 2, not 4. Okay, this should be 2. Okay, I'll take 1 more minute. So what we know about this graph, so first of all, we know that by a result of Dixon showed that if you take even 2 random permutations, then with high probability as n tends to infinity, they generate the entire symmetric group or an. In either case, these groups act transitively on the S tuples when S is fixed. So these graphs are connected with high probability. Now, for S equals 1, Friedman proved that these graphs are not only connected, then they have an almost maximal spectral gap, which means that they're almost, this means that the second eigenvalue of the adjacency matrix is almost as small as it could be. And actually, the same result is also true for S equals 2. This is a much more recent result by Bordenave and Collins. When you act on pairs of elements, you also get a graph which is almost with maximal spectral gap. And I should say that probably this technique can be generalized to every S. to every tuple, but it's not written anywhere. For every S right now, the best result is by Friedman, Zhu, Roichman, Stern, and Tillich from more than 20 years ago. They showed there is some constant which is smaller than D, which depends on S and D. So these graphs form a family of expanders. They have a uniform spectral gap. Okay, so I'll just say what we know. I won't say anything about the proof, unfortunately. So if we use this, we use our results. So we already have, together with, so this was my own work, and then we improved it with Friedman this year. If we use the results about fixed points, we get a different proof to the action on one tuples, on singletons. But now, together with Liam Hanany, we use the new results, and we get a proof that for every S, we have this estimate. Okay, the second eigenvalue is at most is optimal up to this term. And if we know this conjecture that I mentioned before, we could improve it to this thing. So if this conjecture is true, we could have a uniform result, a uniform bound on every S, independent of S. Okay. Yeah. Okay. I think I'm out of time. So good. Yes. So perhaps I'll jump to the last slide. This will also relate to Victor's question. Yeah. Okay. I wanted to sketch how it's related, but I don't have time to do that. So concluding remarks, other groups. So this relates to, so Victor asks if there are analog results for PGLN F, where F is a finite field. So actually we have some evidence that suggesting that there are similar phenomena. I already mentioned UN, ON, and SPN. I mean, I mentioned UN, but this is true also for orthogonal and symplectic, compact symplectic group. And we have some results also for generalized symmetric group, and also for GLN FQ. And this is also true for PGL, it doesn't matter. So you have some partial results in all these families of groups, which suggest a very similar phenomenon. And I will end with this question. So we have some evidence that perhaps what I stated before about the symmetric group is in fact much more general. And for all these groups, if I take some natural families of characters and look at the expected value over W, then we get the same bound that we had, that we conjecture for the symmetric group. Okay.
But what's the character you take specifically? What's chi n? For
So
say GLN FQ, yeah.
For what? For
GLN, yeah.
Okay,
yeah,
so we define you need to take some character. Okay, first of all, you fix Q, you fix the field, and you take the families, and you let n vary. So there are some natural ways to define these characters. One example is, first of all, this should be irreducible characters. So one example is the action on the projective space, on the projective line, actually. It's the project, no, the projective
yeah, so you take
space.
the cuspidal ones, yeah, I see.
No, I don't, no, these are not. No, I take I can take induction from cuspidal. These are not the cuspidal, just cuspidals.
You take induction one, okay.
No. So for example, I can take the action on the projective space. So these are the one-dimensional subspaces of FQ to the n. This is not a trivial. This is not irreducible. But if I subtract, so this action is not irreducible. If I subtract the trivial, this is irreducible. This is, for example, one family of characters, and we conjectured in this case this should be 1 over the dimension is roughly Q to the n, and we conjectured this should be like that.
I see, yeah.